All right. Welcome to the next one. Linear word problems. Essentially, we're going to take the skills that we've been using and we're going to put them to word problems. And this is actually a really fun application because there's a bunch of different situations where we use linear models to describe and predict things. So yeah, we're going to do it, and it's fun. And also, I think that you'll really get an appreciation for the different aspects of linear equations and why we use them and why they're important in this context. Essentially, we're putting to work all the different fun things we've been talking about up till now. I don't know if I'm going to do too much graphing in this, but yeah. So at the end of this, you'll be able to recognize keywords indicating linear relationships. That's super important. Of course, in our class, in this specific situation, you will know that it's linear because it's on the linear test. But, you know, on the final exam or out in the wild, sometimes it's helpful to know. You'll be able to assign dependent and independent variables. Remember all that defining variable stuff? You'll be able to build a linear model from clues, and you'll be able to use a linear model to solve problems. This is a super fun application. Okay, so before we go any further, I want you to know that the most common way, the most common type of model are linear models. Linear models are used to fit data when you're doing data analysis often. They're used to kind of predict what the outcome of a certain situation is going to be. They're super good. And their power lies in the fact that you don't need all that much information to get a linear model, and they're really easy to use. So essentially all you need is 2 data points, and you can build a linear model around them. That said, generally linear models, I mean, not everything in the world can be described with linear models, right? Like fish stocks, that doesn't work. And the world's just full of things that where linear modeling is too simple to describe it. And so in situations where linear models are really good, we tend to see keywords prop up. And so if you can recognize these keywords, you can recognize when we can use linear modeling. They're words like constant rate, right? So somebody will be like, hey, I'm walking down the road at a constant rate, or I'm making cookies at a constant rate. That indicates that there's a linear model. We also see the word proportional, or a variation thereof is in proportion. No, not to, in proportion to, dot, 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 as a keyword. One way to think about proportions is like you're making cookies, right? So in those cases, there are proportions. 2 cups of flour and 3 eggs and 4 cups of sugar. And you can double that recipe by doubling all those proportions. If you want to make twice the number of cookies, you multiply the flour by 2. You multiply, right? So that's what proportion means. If something doubles, you double. It's pretty straightforward. Another one that's a little bit less literal is varies directly. Which means that if you change your input, your output will increase or decrease by a set amount. So essentially, it's a technical word, but it refers to kind of the slope, if you want to think about it that way. Okay. And the last one is linear. I mean, sometimes we're not fancy, and you say this is a linear relationship. So if you hear any of these words in a word problem, or if you're in real life and you're not doing word problems in a specific situation where you want to do some modeling, these all mean that you should be using a linear model. Like I said, linear models are really easy to use. They're really straightforward, but they don't work all the time. You don't want to get over-reliant on linear models, but linear models tend to work in the near future very well. Okay, so the first example of the strengths and weaknesses of linear modeling, here's a question. Terry's height is increasing at a constant rate. When he was 8 years old, he was 3 feet tall. When he was 12, he was 5 feet tall. How tall is he when he's 20? So one way to do this question, I guess, is you could do it graphically, right? So you could be like, time in years, and then height. And then you'd say, okay, when he's 8, 2, 4, 6, 8 years, he is 3 feet tall. 1, 2, 3, so he's that tall. When he's 12, 10, 12, he's 5 feet tall. And then you can draw a line representing his height and answer the question. So that works. I don't like it. I mean, it works, but I'm not going to focus on that type of problem solving right now. Essentially, we're going to do the same thing, but algebraically. So, when we were talking about problem solving in a previous lesson, we were talking about how one aspect of this is defining variables. So we would say, hey, the thing that varies, we'll call that the variable. That's the width of the triangle, or whatever it was in each specific case. You got to decide which piece of information is encoded as the variable. Since then, we've introduced the idea that there's dependent and independent variables. And in this case, it's actually pretty straightforward. When you're interpreting the data, there's one part of the data that depends on the other part of the data. Okay? And so we need to start by formally acknowledging which is which. In this case, your height depends on your age. So this is the age, and y will represent the height. So now we can represent the first data point. When he's 8, he was 3 feet tall, as there was a time when his age was 8 and his height was 3. And then there was a second time when he was 12 and his height was 5. We can use these to make an equation, a linear function, describing his height over time, describing y is a function of x. It's not that tricky. Let's figure out what the slope is. Delta y is 5 minus 3. Delta x is 12 minus 8. So that's equal to 2. So that's equal to 4. So the slope is 2 over 4 and half. And then we can put things in point slope form. Y minus 3 is equal to 1/2 x minus 8. Before I go any further, sometimes it's helpful to test. I've used this data point in my point slope form, so I can test to make sure that this data point works in the equation. So y is equal to 5 minus 3, and 12 minus 8, this is equal to 4 over 2 is equal to 2, and that's equal to 2. Check mark. It works. Okay, so there's my variable. And so the idea here is, you know what, let's put this in point slope-intercept form. So that's 1/2 x minus 4 plus 3, which is 1/2 x minus 1. Wow, when he was 0, his height was minus 1. Weird. Okay, so now I can use my equation in slope-intercept form to answer the question. How tall would he be when he is 20? So when he's 20, so it's 10 minus 1, so it's 9. He's going to be 9 feet tall when he's 20 years old. And you see the power of linear equations. It's very easy to set up a linear equation describing the data. But you also see the drawback. Sometimes it doesn't make sense. I mean, it could be 9 feet tall, but I'm not betting on it. It's probably something wrong with the overall idea of fitting this data to a linear equation, but whatever. It also works in other cases. This one will work a little bit better. Beatrice is jarring jam. So she's making jam, putting in jars. A steady rate of 8 cans every hour. I guess 8 bottles? Jars. Every hour. At 9 a.m. she's made 28 jars of jam. When did she begin making jam? And at what time will she make 40 jars of jam? Okay, so how can we tell this is a time for a linear model? This is the keyword, steady rate, okay, or constant rate. So I'll talk about how to interpret this in a second, but let's start by defining what our variables are. We have x, which is independent, and y, which is dependent. Let's call the independent variable the time. And y is the number of jars full of jam currently. Okay, so I need to put this data into an equation. Let's find our data points. At 9 a.m. she's made 28 jars. That's one data point. What's another data point? There is no other. Instead, we get an expression like this. A steady rate of 8 jars every hour. If we were to graph this, solve this graphically, the first data point would be, I don't know, somewhere over here. 8 jars every hour. That means that 1 hour later, she would have made an extra 8 jars, right? This expression of what the rate is, it tells us what the slope is of our function. In other words, you don't have to bother with all this graphical stuff. You can just read off the slope from the expression. Slope is equal to 8 jars per hour. It's the ratio of how the number of jars on the table is increasing depending on how the time is changing. So now I can use point slope form to write out this expression. 28 is equal to 8 times x minus 9. Okay. So this is an equation we just found modeling how many jars of jam she has made. How do we use it? Well, let's answer this question. When did she begin making jam? Well, y in this case is the number of jars of jam, and x is the current time. So when she began making jam, the number of jam she had on the table was 0, right? And so I can use that to figure out what value of x, the time, she started. .5. Okay, so that's in hours. So she started at 5:30 a.m., which is pretty early to start making jam, but I guess whatever you want. At what time will she have made 40 jars? Well, y is equal to 40. I can solve that. 8x minus 44. So this becomes 84 is equal to 8x, which becomes x is equal to 84 over 8, which becomes 84 minus 8. All right, so she'll have 40 jars of jam at 10:30 a.m. This question, I wrote the answers in terms of the time. That's just to make sense to you. In terms of your overall answer, if this was a test, these numbers would do. They'd satisfy me. I don't care. But I just wanted to make sense of the question for you. So, whatever. All right. I like this question because it emphasizes some of the finer points of what we're working on. The number of towels we need to stock at our camp, we've got a kids camp, varies directly with the number of kids attending our camp. Look, varies directly. That means that we're probably going to have to use a linear model to describe it. If we have 3 campers, we need 9 towels. If we have 8 campers, we need 19. Oh, hold on. Towels. Sorry, I changed it to I copied down the word wrong. How many towels will you need if there are 200 campers? How many towels does each camper get? So the impulsive thing to do would be to divide 9 by 3 and say each camper gets 3 towels. But if we did that, then if there's 8 campers, 8 times 3 isn't 24, but I said that 8 campers is 19 towels. What's going on here? So it turns out that linear relationships allow for a little bit of subtlety that I'm going to go into in a second. Essentially, let's just start it the way we have before. X, Y, independent, and dependent. So what's independent? Independent is the number of kids. Y is the dependent one. It's the number of towels. Okay. So the first data point is if you have 3 campers, you need 9 towels. And the second data point is if you have 8 campers, you need 19 towels. So the slope here, delta y, is equal to 19 minus 9, so that's 10. And delta x is 8 minus 3 is equal to 5. So the slope is 10 over 5 is equal to 2. So in point slope form, the equation here is y minus 9 is equal to 2 times x minus 3, 2x minus 6 plus 9, y is equal to 2x plus 3. So we can use this question, we can use this model of how many towels you need, which is y, depending on the number of campers, to answer the question. If there are 200 campers, how many towels do we need? Well, y is equal to 2 times 200. You just replace the x with the 200, which is 403 towels. How many towels does each camper get? Let's look at this equation, because this equation's fun. If x is the number of campers and y is the number of towels, then each camper gets 2 towels. They come to camp and we say, here are your 2 towels, don't lose them. Right? What's up with this 3? Well, I don't know, maybe like the counselors need towels too. But they won't lose theirs, so maybe there are 3 camp counselors and each of them gets a towel. Each of the counselors get 1 towel maybe, and then each camper gets 2 towels. You see? There are extras that aren't going to the campers. That's what our model tells us. So linear models, a sophisticated linear modeling system lets you see this information in the data, even if you wouldn't expect to look for it otherwise. How about this one? The number of sales we make, I guess I'm working for a company. The number of sales we make increases in proportion to the amount we spend on advertising. If we spend $100, we get $300 in sales. If we spend $400 on ad, we make $900 in sales. How much should we spend to get $2,000 in sales? How to do that? Well, what depends on what? maybe the sales depend on the advertising. The more you sell on advertising, the more you get in sales. So the first data point is 100 in advertising, you get 300 in sales. And the second is 400 in advertising, 900 in sales. Okay? So delta y is 900 minus 300, so that's $600. And delta x is 400 minus 100, that's 300. So the slope, delta y over delta x, is 600 over 300, so that's 2. Every dollar you spend on advertising, I guess, gets you $2 in sales. So y is equal to, wait, hold on. We need to put this in point slope form. Minus 300 is equal to 2x minus 100. Okay. 2x minus 200 plus 300. So y is equal to 2x plus 100. So we can use this to answer the question. I want y to be 2,000. 2x plus 100, which becomes 1900 is equal to 2x, which becomes, I have to spend $950 to get $2,000 in sales. Before we go on, I want to point something fun out to you that our model has resolved for us. Every dollar spent in advertising gets back $2 in sales, right? But if you spent $0 on advertising, you'd still make $100 in sales. Maybe that's foot traffic, something that doesn't depend on advertising. Or maybe your mom just buys cookies from you or whatever you're making. Whatever the case, there's some part of your clientele that doesn't depend on your advertising. All right, one more question. It's late afternoon and all the trees have shadows which depend linearly, whose length depends linearly on their height. A 1 meter tree has a 3 meter shadow. A tree of 3 meters has a 7 meter shadow. How tall is the tree with the 201 meter shadow? Okay, so how does this work? X, Y, independent, dependent. What do you think the independent variable be? What do you think the dependent one should be? Let's make the dependent one the shadow length, and the independent one the tree height. Okay? And the first one is 1 meter tall, 3 meter shadow. And the second one is 3 meter tall, 7 meter shadow. All right. So delta, maybe I'll do it over here. Delta y is 7 minus 3 is equal to 4. Delta x is 3 minus 1 is equal to 2. The slope is 4 over 2. The slope is 2. And so in point slope form, this expression becomes y minus 1 is equal to 2x minus 3 . 2x minus 5. Weird. No, that's not right. Oh, you know what? I see what I did wrong there. I switched them. The independent variable is the height. So a 1 meter tree has a 3 meter shadow. There we go. So y is equal to 2x minus 2 plus 3. Y equals 2x plus 1. Okay, cool. How tall is the tree with the 201 meter shadow? So 201 meter shadow. So that becomes 200 divided by 2x. So 100 is equal to x. Well, that's interesting. Oh, wait, hold on. Does this make sense? What's with that 1? How can... I mean, that means if something is no height, it will have a 1 meter shadow. I don't know. Maybe all these trees are on like a... Maybe they're on like a cliff where they project some shadow down here. So even if they don't have height, the cliff casts a shadow. Maybe that's what's going on. I don't know. But long story short, the linear equation took care of us. So, long story short, let's review. Defining variables is an important aspect of this. Essentially, we've got two variables now to work with, x and y. One of them's dependent, the other's independent. We're thinking about this in a slightly different way than function notation, but the idea here is that we've got two pieces of data. For each dependent variable, or each independent variable, I have a dependent variable. The data points come in pairs, right? So I can assign those, and then I can use those to set up the model of a linear equation. You can rearrange the model and interpret the model. You can interpret the linear equation. It tells you stuff about what you're working on. And then you can also, use it to solve problems. Okay, so that's it for lesson number 3. Maybe I can make another lesson or two before I go home today, but that's it for lesson number 3. I'll talk to you later. Have a nice day.